This is the second lecture out of 3, and the first lecture is posted on the website already, and we'll post homework as well for the students, hopefully tomorrow or Thursday. So last time we looked at how material respond to oscillating electromagnetic wave, and we saw that we could describe these interactions using a single optical parameter here, which is a complex parameter, the complex refractive index. So there is an imaginary part, which is the expansion coefficient, and a real part, which is the real refractive index. And so we saw that the expansion coefficient is associated with friction or dissipation of the light energy. When the light wave couples with the oscillator, the energy is being dissipated, and that corresponds to that the imaginary part of that index. And so for fast oscillating wave, it will couple with oscillators that are light, which are electrons in that region. So in fast oscillating range of the electromagnetic wave, typically the UV. And for the slowest wave, they will couple with heavier oscillators, which are in that region in the infrared, which are the atoms. So the whole atoms are going to oscillate. So in both cases, we have strong coupling of the light and strong dissipation of energy. In the center, we are far away from the resonance frequency of either the atoms or the electrons, and in that case, we don't have dissipation of energy. However, the electrons are still able to follow the oscillating field, and that generates things like reflection, which are measured by the refractive index. So we have our complex refractive index here with two parameters, the imaginary and real. Now, what we are really interested in is in actually measuring in the lab experimentally these parameters. So typically, to get N, you'll measure reflection, and to get K, you'll measure the absorption coefficient. Directly related K, the expansion coefficient, is directly related to the absorption coefficient. So in order to do that, the proper tool to measure this coefficient are spectrometers, but we saw that there are no spectrometers which is capable of covering, spanning the whole range of wavelengths, or at least the optical range of wavelengths, from the UV all the way down to the infrared, going through the visible, which is typically the span of wavelengths that you'll be interested in for that we are interested in for optical materials. So in that case, you need two types of spectrometer. So we saw that for the high energy range, we need a UV visible spectrometer, and for the low energy range, we'll need an infrared spectrometer. So I think it's quite important, especially for a student, to get familiar with especially when you get involved in research activity, to get familiar with the tools that you use and to understand pretty accurately the tools that you use to do experiment and to make these measurements. So I want to describe these spectrometers for a little bit. In most spectrometer, you'll see 3 basic parts. So the first part is going to be the light source. You'll need a source of light which is, as depicted here, as wideband as possible, which means you want to emit light over the widest range of wavelengths as you can. And the reason for that is because you are going to send all these wavelengths through the sample and see what's coming out and what does not come out, and that will give us our transmission spectrum. In order to do that, we will need a way to select the wavelengths and to separate the wavelengths, and that's done using a monochromator. What I've depicted here is a prism. This is very old-fashioned. Nobody uses prism anymore. That was back in the 19th century. So we have far more efficient ways of separating light using gratings now. The third thing you'll need is once you've separated all these wavelengths, you want to measure the collect or detect the light and detect the light, but also measure its intensity. So to do that, you will need a detector that's capable of measuring the light in the specific range of wavelengths emitted by a given source. So as we saw, there is no single spectrometer that's capable of scanning the whole range. So we have two types of spectrometer to consider. And my first type of spectrometer is going to be the UV visible and near IR, often span as well near IR. So this type of spectrometer is typically going from about 180 nanometer, which is well into the UV, ultraviolet, all the way down to about 3000 nanometer, which is 3 micron, which is well into the near IR, almost the mid IR. So we want to scan that entire range. So in order to do that, we're going to need, again, a light source. So to scan that whole range, there is no single light source which is efficient over the whole range. So we'll need actually two light sources.